Hello, my name is Josh Verghese, and I'll be reviewing the capstone project that I performed over the past 2 terms. The goal of the project was to create a wireless water activity monitoring system. Both the capstone project and this review were advised by Dr. John Akin. The agenda for today will be to go through the introduction, which will cover the team that I worked with alongside what exactly a capstone project is. The background section will go over what the project applications were, and then the research section will go through what we needed to find before we could go into the methods and testing. And then we'll move through that methods and testing, and then the results section will cover what we actually found, and the conclusions will go over an analysis of those results. A capstone project is something that most electrical and computer engineering students need to complete. It's a culminating engineering project that allows us to use a lot of the experience we've learned from school and put it into practice in a industry setting. For my team, we had 2 electrical and 2 computer engineering students. I was one of the computer engineering students, and we were advised by Dr. John Akin and sponsored by Dr. David Burnett from PSU's Wireless Environmental Sensing Technology Lab, or the WEST Lab. This is a lab that focuses primarily on wireless communications, low power radio frequency, and environmental sensing systems. My area of focus was being one of the 2 computer engineering students. I had to serve as sort of the bridge between the electrical and software sides of the project. Moving to the background section of the project, it is based on carbon sequestration, which is a method that is used to take in carbon from the environment. And basically there are capsules that are buried underground and filled with biomass. And this biomass is plant matter, food matter, or waste matter. And the capsule is sealed and put underground, but our industry sponsor wanted us to focus on wood for the material because it was more applicable outside of this specific scenario. One way to allow the material to last a little bit longer is by measuring using a metric called water activity, which can help determine if a material will be affected by microorganisms. So a problem we were facing was that the biomass needs to be dry enough so that microorganisms cannot live in this environment, which could decay the wood and lead to a quicker release of carbon. And then on top of that, people maintaining these capsules need to have confidence that there are no leaks, since the capsule needs to remain enclosed the entire time. And finally, the research on water activity of wood is very sparse, so all of this really was new research. Our project goals were to create a device that can measure the water activity of wood based on our project applications. Data collected from measurements needed to be transmitted through OpenWSN, which was a software that was created by UC Berkeley for wireless communications. The main focus of it is low power applications, which was really important for our project. Alongside this, water activity data needs to be graphically represented, and the device needs to be affordable in comparison to commercial devices. Most of the devices on the market range from hundreds of dollars to over $10,000. And so this was also another critical part of the project, just getting the price down well below these current offerings on the market. Lastly, the device needed to use a relative humidity sensor and a moisture content sensor, one or multiple, to find the water activity within the wood. Moving to the research section, water activity is a measure of the free water that is available for microbial growth. It basically measures the water that is not bound to a food. After going into a little bit more research, we were able to find the equation that you see here, which relates relative humidity to water activity. And this ERH value is the equilibrium relative humidity, which basically requires us to measure the air in an enclosed environment with the food at the bottom of the enclosure. And when the values stop changing, then you know you've hit equilibrium with the air and the food. So this equilibrium value divided by 100 gives us the water activity. And this was really important for the initial parts of our research. The other main part of our research involved finding humidity sensors. The first sensor that we found was the DHT22, which is a relatively cheap humidity sensor. It was the cheapest of the 3 that we found, and also had the least accuracy and the most sensor drift. So eventually the sensors will not be fully accurate and they'll drift from their expected values or their expected accuracies. And this one had the greatest drift of the three. We mainly intended to have this sensor as a comparison to the others since we had used it in previous classes and labs. The second sensor actually was the most expensive option, but still not far off from the DHT22 price-wise, and it was the ideal option for our project since it connected really well with the network that we were using and seemed to have the highest accuracy readings and lots of low power modes to increase the life of the sensor. So this was another big focus of the sensors. And then the last sensor was the BME 280, and it seemed to be right in the middle of the three regarding accuracy and power management. Moving to the methods and testing section, our test plan revolved around two primary tests. The first was a sensor confirmation test, which we basically placed the sensors in an enclosed environment. And you can see in the images to the right the basic setup. We basically placed the sensors inside of these containers, which were placed inside a cooler for temperature control. And from here, we measured the equilibrium relative humidity and converted the water activity value based on that equation that I showed earlier. We measured against a database of foods with known water activity values, and these foods had specific brands associated with them. The second test was to create a moisture isotherm curve, and the reason for this was this curve compares moisture content and water activity. Since there was no clear relationship from the research that we did between water activity and moisture content. So we had to make this curve, take multiple points on this curve and find the material moisture and that relation to water activity. So to do this, we had to use the oven dry method to measure the moisture content accurately. This relied on drying the wood in an oven in multiple stages, weighing the wood before and after drying, and then comparing these two weights. We then plotted the moisture content against the water activity and displayed the curve. So the initial results of our test actually showed that the DHT22, which we had been having the least expectations about, was providing the most accurate results. However, there were a few factors affecting the SHT45's readings, and the sensor seemed to need a higher food to air ratio, which was something we discovered later in our research. And for some reason, the DHT22 was producing expected results at this lower food to air ratio and unexpected results at this higher ratio. And then measuring the wood in the enclosure similarly to the food actually produced really close results for both of these sensors. You can see that here in these tables where comparing the same exact wood for the SHT45 and DHT22 sensors, we start at 89.97 and then 92.4% relative humidity for the wood, and as you go down that list, it continues to align very closely. And then we see a similar pattern for the other woods, and then at the bottom you can see our moisture isotherm curve, which was comparable to expected results. Finally, the conclusions for our project required us to look at these odd discrepancies that we were seeing at first. Even though the SHT45 was our ideal sensor, it was producing unexpected results at first. And we found that fixing this ratio of food and air was able to take care of that. And a smaller ratio can either take extremely long to reach equilibrium, or it may never reach it at all, which could have been what was causing us some of our unexpected readings. It's still a little bit difficult to explain why the DHT22 wasn't producing these expected results at these higher measurements. But moving forward, some important points are that we believe that we can expect accurate values for water activity data from these cheap sensors when we're measuring wood, despite not having any additional data to go off of. Using this high wood to air ratio, as we did with food, gives us increased confidence in our tests. Although future research in this space might include more tests to increase confidence in our setup, alongside just general improvements in sensor technology that can help make these cheap sensors more reliable. Here is my resources that we use in our project and that I use in my paper. And yeah, thank you so much. I'll open up to questions.